When you guys start with question 4, guys.
You want to stop that here?
Nice stapler.
This one will be. This one.
It's pointing up.
Okay, so this one. This one. That's what I've been told.
Alright, guys. When you do for question 4, guys, this week we do question 4, 5, and 6 from sheet number 4. Right? There are only 4 questions, guys. I guess some of you have already done this, so. Alright, just start with question 4, guys. I'll give you a couple of minutes and see if you can do it. Okay, for this one, yeah, you find the MLE for tau, you just replace lambda by lambda hat. So you just replace lambda by lambda hat to find the MLE for tau. Very simple. This is the content of the library. You find the MLE for this one.
Yeah, I don't know what different. Have you got some hope? To expand them?
Yeah, you should know that it's standard according to number, then you can start with it. You guys done question 4 or what? Anybody who hasn't done question 4, guys? So let me show you how to do it. It's really not difficult. You have you guys done question 4, guys? Not yet. Not yet. Okay. So you have
No, this pen is not working. All the pens I use are not working.
so you have a sample x1 to xn IID from a normal distribution with mean equal to alpha plus beta, variance equal to 1. Now, if you guys been coming to my lectures, you will see that this implies that the MLE of alpha plus beta, right, is equal to the sample mean x bar. Do you guys know how I got this, guys? Because remember one of the questions I did in the lectures was that if you have a random sample from a normal distribution, the MLE for the mean parameter is equal to the sample mean. So in this case, the MLE for alpha plus beta is equal to the mean of the sample x bar. Yeah, and this implies that the MLE for alpha plus the MLE for beta is equal to x bar. Yeah, and similarly you have another sample y1, y2 to yn IID coming from a normal distribution with the parameters alpha minus beta and 1, right? So in this case, by using the same principle, right, or using the same argument, the MLE for the mean parameter, which is the MLE for the mean parameter, which is the MLE for alpha minus beta, is equal to the sample mean, which is y bar. So that implies that alpha hat minus beta hat is equal to y bar. All right. So call this equation 1. Call this equation 2. Now you have two. You have two equations and two unknowns. Solve them. So if you add equation 1 and equation 2, you get 2 alpha hat equal to x bar plus y bar, and therefore alpha hat is equal to and if you do equation 1 minus equation 2, you get 2 beta hat equal to x bar minus y bar. So beta hat is equal to this. So this is the MLE for alpha, and this is the MLE for beta, guys. Is that clear? I mean, this is not the only way to do it. You can do it in other ways too, but this is one of the simplest ways to do this question, guys. Is that clear or no? Yeah. You guys okay, guys? And you do question 5, please, now, if this is okay. You guys do the next question, guys.
We got in a last week.
You guys do question 5, please. You guys okay? Did you guys all sign the attendance sheet? Anyone who hasn't signed? We have. Okay.
Oh, sorry.
Oh, sorry. Sorry, man.
Sorry, no, right. It's hiding in the corner.
Sorry.
Thank you.
You guys signed it?
Yeah.
The question 5 involves the gamma distribution, which is given in the lecture notes. So the PDF of the gamma is on page I think it's page 8. If I read it correctly. If you look at page 8 of the lecture notes, you will see the density function of the gamma distribution. Page 8, equation 35, 35. Yeah, can read it. Sorry. So you have x1, x2, all right, so you have a random sample from a gamma distribution with these parameters. And excuse me, you're assuming that R is known. So the only parameter that is unknown is the parameter lambda. And we want to find the MLE of the parameter lambda first. So the first thing you need to write down is the likelihood for lambda. And if you look at page 18, page 8 on equation 35, you will see the you will see that the likelihood function is the following. Can you guys see this formula on page 8, right? Yeah. So this is the this is a product of this density function from 1 to n. Now if you simplify this, guys, you get, once again, simplification of likelihoods is a very important thing. I think I mentioned this many times. All right, this is what you will get after simplification from this to this, right? The next step is to take the log of the likelihood. Alright, and the next step is to, because there's only one parameter, you just need to find the derivative with respect to only lambda. Yeah, so the derivative of this is this. Set this to 0 and solve for lambda. You get lambda hat equal to nr divided by the sum of xi, which is the same as saying that r divided by the sample mean. Now, to make sure that this is an MLE, remember when you have only one parameter, you must show that the second derivative is negative. So the second order derivative with respect to lambda is minus nr divided by lambda squared, which is of course negative all the time, and hence lambda hat equal to is an MLE. Now to find the MLE of tau, you are told that tau is a function of lambda. So the MLE for tau is what you get by replacing lambda by lambda hat. So the MLE for tau is simply this, which is 2r divided by x bar minus 1 squared. So this is the MLE for the function tau of lambda. Is that clear, guys, or not? You guys okay? All right. Can you do question 6, please, now? If it is okay. Yeah, it's a function of lambda. This is r, madam. This is r. This is tau. This is tau. This is different symbol. This is tau. This is r. They're two different symbols. Yeah. Yeah. The question will say whether it's IID or not. I think in all the questions you will get the data will be IID. Yeah, the data will be IID. Yeah. Are you guys okay with this or not? How are you guys doing? Okay. If it's a parameter, solve for these possible parameters and give expressions for the MLE of R and MLE of F. Yes, yeah.
I mean, it's natural. So just this is the partition, but
And you guys do question 6, please.
You're also you're reading the Bible or what?
MLA is just a method for estimating parameters. Yeah, like when you have a data set and you want to know, you want to estimate the population parameter, like the mean height of all people living in the UK. It's impossible to access the whole population. So we draw a sample and we try to estimate the sample based on the sample. We try to estimate the mean height. MLE is a method for doing it. And so the principle here is to first write down the likelihood function and then find the parameters that maximize the likelihood function. Maximize the likelihood function. Like with this question 4, we already knew that the sample mean maximizes the likelihood function. Alright, so that's why we said the MLE for alpha plus beta is S bar. And MLE for alpha minus beta is y bar, because we knew that the sample mean will give the maximum value for the likelihood. The likelihood function is just the product of the density functions of the data. Right. The likelihood function is the product of the density functions of the data. So when you have the x's, x1 to xn, we know that from the examples we did in the classes, the sample mean x bar maximizes the likelihood function. And similarly, when you have the data on the y's, the sample mean for the y bar maximizes the likelihood function for the y's. And based on those two, I can derive the value for alpha and beta.
We write down the likelihood.
Yeah, you can do it like that too. Right? You get the same. Yeah. Yeah, you get the same result. Yeah, yeah. Yeah.
Bring it back.
Yeah.
Bring it back to
Yeah.
that. So we can run that.
All right.
That's what you can do.
You guys okay or what? Some people appear confused. I don't know. In just to go back to question 4, guys. Just to go back to question 4. Remember, we had x1, x2 to xn IID with parameters, with normal distribution, and y1, y2 right? We had this situation in question 4, guys. Now, the way I did it, the way I showed you the solution is the simple way. There's another way you can do this question is to write down the likelihood for alpha and beta as the product See, another way to do the same question 4 is to write down the likelihood function, which is this times this, all right? Then take the logs, and then take the partial derivatives and solve the two equations, and eventually you will get the same answer that we got earlier, right? So you write down this likelihood function, then you solve the equations that the log of you solve these two equations that the partial derivative of the log with respect to alpha and with respect to beta are equal to 0. And if you solve this equation, you will get the same answers that we got earlier. That is, what answers do we? Yeah, we got the answers that alpha hat is equal to x bar plus y bar divided by 2, and beta hat equal to x bar minus y bar divided by 2. But this is a kind of a long way to do it, because you have to first write down the likelihood, simplify it, take the log, take the partial derivatives, set them to 0, and then you get the answers. So it's a kind of a long way to do the same question, right? That's why I didn't want to do it this way. But now, returning to question returning to question 6, guys. Let's see. Returning to question 6. In question 6, we have x1, x2 up to xn IID exponential with parameter lambda 1, and then you have y1, y2 up to ym IID with exponential with parameter lambda 1, lambda 2. Now, to do this question, once again, you can take the long approach. The long approach would be to write down are you guys listening to me? The long approach is to write down the joint likelihood function, which will be the product of lambda 1 times is to take the product of these two, and this will be the joint likelihood function of lambda 1 and lambda 2, and then take the log, and then take the partial derivative with respect to lambda 1 and the partial derivative with respect to lambda 2, set them to 0, and solve these two equations to get lambda 1 hat and lambda 2 hat, right? This is the long way to do this question number 6. But the shorter way to do the same question is as follows, right? The shorter way to do the same question is, instead of taking this long approach, guys, what you do is the following. So we know that x1, x2, right, guys, is from IID exponential with parameter lambda 1, which implies, if you look back in the notes, guys, we did the I think 2 or 3 weeks ago we did the MLE for the exponential. You may remember that the parameter, the MLE for the lambda parameter for the exponential distribution is 1 divided by the sample mean. So in this case, this is 1 divided by x bar. Do you guys remember this result from, I think we did this way back 2 or 3 weeks ago? Yeah, yes, no? Yeah. All right, and similarly, if you have y1, y2, if you have this, then by the same argument, the MLE for lambda 1, lambda 2 is 1 divided by y bar, which is the same as saying that the MLE for lambda 1 times the MLE for lambda 2 is 1 divided by y bar. Now call this equation 1, call this equation 2. We should divide equation 2 by equation 1. You get lambda 2 hat equal to x bar divided by y bar, right? And lambda 1 hat is of course 1 divided by x bar. All right, guys. This is the shorter. I don't know whether you get my point, guys. This is the shorter way to do the same question number 6. The longer way is to write down the likelihood function of lambda 1, lambda 2, take the log, take the partial derivatives, and solve the equations. And that will take you a lot longer than this approach, right? Is that clear, guys? Yeah. All right. Can you do just one more question, guys? Question 7. Yes.
Why would you ever do the long approach then? Unless,
Why?
Yeah, why would you do the long approach? Unless you didn't have the distribution.
Yeah, I mean, you don't want to do the long approach. You take a lot
Yeah.
longer. Yeah, I mean, in this case, it would be much better. But for certain distributions, you need to use the long approach.
Where you don't have the.
Yeah.
Yeah.
For certain distributions, you cannot do it this way. You have to use the long approach.
Okay.
Yeah. You guys do 7, please. this is a function of mu, the MLE for this is what you get by replacing mu by time. That's what this property says. All right, guys, could you listen, please? Question 7. You have x1, x. All right, now the question is to find the MLE for delta. All right, let's try the standard approach. The standard approach will give you sorry guys. Yeah, and this will be E of n delta. Yeah, so the log of the log likelihood function is n delta minus the sum of xi. So the derivative of the log likelihood will be n, which is equal to 0. Doesn't make any sense, right? So that means the standard approach doesn't work. So we need to use the try the indicator function approach. All right, guys, because the standard approach has that has no sense, right? So the indicator function approach, when you write down the likelihood function, guys, you need to make sure that you put, remember that x must be greater than or equal to delta. So you put the indicator function that every xi is greater than or equal to delta, guys, right? So this is what you need to do when you write down the likelihood function under the indicator function approach. So this will be E n delta minus the sum of xi times the product of the indicator function. Now remember, there are three rules I gave you in the lecture notes to simplify products of indicator functions. I hope you guys remember those. Now what would this simplify to, guys? This one here, what would it simplify to? It would simplify to Come on, guys. I thought I gave you the rules, guys. Just look back in the lecture notes, guys. It would simplify to the minimum being greater than or equal to delta. All right. The next thing you need to do is to draw a graph. This is where your your skills comes in. Suppose this is delta. Suppose this is L of delta, and suppose this is your min of xi. Now, if you draw the graph, guys, how do you think it will look like? This is you guys being experts in calculus, you see there's only one delta here. And there's an n in front of it, which is a positive constant. So that means that this guy here is an increasing function of delta. So how would it look like, guys? And delta must be less than or equal to the min of xi. So if this is the min of xi, your graph will look like this, and thereafter it will be 0. Can you guys see this or not? Huh? Yes? No? Because n delta is n is a positive constant, n delta is as a function of delta is an increasing function, right? So it's an increasing function up to this point, and once you pass this point, this is no longer true, and therefore it will be 0. And the largest point of this graph is over here, right? And therefore the MLE of delta is equal to the min of xi. All right, guys? Is that clear, guys, or not? I'll see you guys in a minute.
Sorry. There, go for it.
It will not be infinity because remember when I can't read it, I need to grasp it. Sorry guys. Sorry. You're asking about this, right? Yeah. So this is versus b. So as a function as when b is equal to the max, it will be a finite number because it will be a finite number, so it will not be infinity. So when you put b equal to max into this expression, you get a finite number, not infinity. So it will be a finite number. Yeah. And the same thing here too. Yeah. But you don't need. But what you should look for is the largest point of the graph. You don't need to worry what is here or not. Just look for where the graph reaches the largest point. That's what you should look for. It's equal to 0 because remember when a is greater than the min, this is no longer satisfied. And so when a is on this side, that is a is greater than the minimum. This is false event. Therefore, this whole thing is 0. That's why it's 0. Yeah. See. Right, so I need to go to the
Oh,
so
I'll send you a mail to just detail the project.
okay, okay.